second speaker is Jason Schweinsberg, who's going to tell us about rigorous results for a population model with selection.
Okay, thank you very much. I'm going to speak about some rigorous results for a population model involving selection. I'll begin with just a very brief overview. Mathematical population genetics is basically the study of mathematical models of evolving populations. And the goal is to be able to compare the predictions that we get from these models to what's observed in actual biological populations, and then use that to draw inferences about how populations evolve, and more specifically, the causes of genetic variability within a population. In this talk, I'm going to focus on natural selection. The idea is that each individual in a population has a certain fitness level, and that gives some individuals in the population a selective advantage over others. A difference between this talk and Allison's talk earlier this morning is that I won't be concerned with spatial structure in this talk. So here's the population model that we're going to consider. So as in many standard population models, we'll assume that the size of the population is fixed, and so there will be capital N individuals in the population at all times. We assume that each individual independently acquires mutations at times of a Poisson process of rate mu sub n. So mu sub n is the mutation rate per individual. We'll assume that all mutations are beneficial. So an individual that has j mutations at time t, which I'll call a type J individual, has fitness 1 plus Sn times j minus m of t, where m of t is the average number of mutations of the n individuals at time t. So for example, if an individual has 3 more mutations than average, then their fitness will be 1 plus 3 times Sn. So the parameter Sn is measuring the selective advantage that an individual gets from a mutation. Now we'll assume that each individual independently lives for an exponentially distributed time with rate 1. And then when an individual dies, a new individual is born, and we choose an individual at random from the population with probability proportional to fitness to be the parent of the new individual. So individuals with higher fitness are more likely to have offspring. Now, although this is just about the simplest model that one can imagine of a population acquiring repeated beneficial mutations, it turns out that quite a bit remains unknown about how the population in this model actually behaves. So I'm going to be focused primarily on 3 questions. First, what is the speed of evolution? That is, how fast does the mean number of mutations in the population grow as a function of time? Second, what is the distribution of the fitnesses of the individuals in the population at a given time? So in other words, if we recorded the fitnesses of the n individuals in the population and plotted these numbers in a histogram, what would the histogram look like? And then third, how can we describe the genealogy of the population? If we took a sample of individuals from the population and followed their ancestral lines backwards in time, what's the coalescent process that describes how those lineages merge as we follow them back in time? Now there's one case in which this model is easy to study, and that is if mutations happen slowly enough that at a typical time there will be no more than 1 mutation in the population that hasn't already spread to the entire population. This will be the case, for example, if the selective advantage S is some fixed positive constant and the mutation rate is much smaller than 1 over n log n. So in this case, we have mutations happening at rate n times mu n, so the number of individuals times the mutation rate per individual. And after a mutation occurs, the number of individuals that have acquired this mutation moves up and down like an asymmetric random walk. With probability approximately S, this random walk reaches n before 0, which means the beneficial mutation has spread to the entire population, an event which is known as a selective sweep. So basically, we have an exponentially distributed waiting time with rate approximately n times mu sub n times S until the first selective sweep. Then we have another exponentially distributed waiting time until the next selective sweep, and so on. So that's a fairly simple picture. However, as soon as mutations happen faster, so that there can be more than one mutation in the population at a time, the analysis of the model gets much more complicated, and surprisingly little is rigorously known. Now, there has been quite a bit of previous non-rigorous work on this model, much of which is very precise and detailed. I've listed here several important papers, of which the paper by Desai and Fisher is the most closely related to what I'm presenting today. So all of these authors obtained precise estimates on the speed of evolution, and they also concluded that the distribution of the fitnesses of individuals in the population at a fixed time is approximately Gaussian. And this leads to the idea of a Gaussian traveling wave, which I've pictured here. So perhaps at some time t1, the distribution of the fitnesses in the population looks like this, with individuals having fitnesses in this range. But then as time goes forward and the population evolves, the fitness of the population is increasing. So at some later time t2, the distribution of the fitnesses may be over here. So basically, as time goes forward, the mean of the Gaussian distribution is moving ahead at constant speed. Now, nothing was known about the genealogy of the population until 2 years ago, when Neher and Hauschak and Desai, Walchak, and Fisher argued that the genealogy of the population can be described by a process called the Bolthausen-Snittman coalescent, which I will define a bit later. So my goal has been to carry out a mathematically rigorous analysis of this population model and to establish, for some range of values for the parameters mu n and Sn, rigorous results pertaining to the speed of evolution, the Gaussian shape for the distribution of fitnesses, and the genealogy of the population. Now, there has also been some previous rigorous work on this model. Durrett and Mayberry considered the case where the selective advantage Sn is a fixed constant S, which does not depend on n, and the mutation rate behaves like n to the power minus beta, where beta is between 0 and 1. And they showed that if t sub j is the first time that some individual in the population has j mutations, then tj minus 1 over log n is converging in probability to some constant little tj. So basically, it takes order log n time for each new type to appear in the population, and so the speed of evolution is of order 1 over log n. They also were able to calculate the distribution of fitnesses in the population at a typical time. However, their mutation rates were sufficiently low mutation rates, that the number of types present in the population at a typical time was just some finite number that does not tend to infinity with n. And so they were not really able to observe a Gaussian shape for the distribution of fitnesses. Now, sort of another extreme is to consider very fast mutation rates, where both the selective advantage Sn and the mutation rate mu n are positive constants that do not depend on n. Etheridge and Cuthbertson considered this case for a model that was slightly different from the one that I presented. They obtained a lower bound on the speed of evolution of order log n to the power 1 minus delta, and a bit later Michael Kelly studied the same model and obtained an upper bound on the speed of evolution of the order log n over log n squared. So for the work that I'm presenting today, we're going to need the following three assumptions on the parameters mu n and Sn. Now, I realize that they're not easy to understand in this form, but these assumptions imply that the selective advantage Sn is tending to 0 as n goes to infinity, and the mutation rate mu n is tending to 0 much faster than any power of Sn, but more slowly than any power of 1 over n. So, for example, if the mutation rate is e to the minus log n to the c, where c is between 1/2 and 1, and the selective advantage is smaller than 1 over the square root of log n, but larger than e to the minus log n to the d, where d is between 0 and 1 minus c, then the assumptions will be satisfied. So you can just think of that case for something more concrete. Basically, the first assumption is telling us that the number of distinct types in the population at a typical time is tending to infinity as the population size n goes to infinity. It's that assumption that's violated in the work of Durrett and Mayberry. The second assumption is saying that mutations can't happen too fast, and we'll be coming back to that later. The third assumption says that the difference in fitness between the fittest and least fit individuals in the population tends to 0 as n goes to infinity, so that we're not getting very strong selection. And although the mutation rate and the selective advantage do depend on n, I'm going to drop the subscript from now on to lighten the notation. So we want to think about how this population model behaves. We're going to let xj of t be the number of individuals in the population at time t that have j mutations. And let's first think about what happens near the beginning of the process when most mutations have not yet acquired mutations. So the number of individuals with 0 mutations is close to the population size n, and the mean number of mutations in the population is still close to 0. So when those approximations hold, we can approximate the individuals who do have mutations by a multi-type branching process in which a type j individual gives birth at rate 1 plus j times s, dies at rate 1, and mutates to type j plus 1 at rate mu. So then if we want to calculate the expected number of individuals with 1 mutation at time t, we can observe that mutations to type 1 are happening at rate mu times the number of type 0 individuals. And if such a mutation happens at time u, the number of descendants of this mutation alive at time t will be roughly e to the power s times t minus u. This individual has a selective advantage of roughly s over most of the population, so we get this exponential growth. And then if we approximate this expectation by n and integrate over u from 0 to t, we get approximately n times mu times e to the st minus 1 over s. And just repeating this process inductively, we can get this approximation to the expected number of type j individuals at time t. Now, when is this approximation valid? So this approximation is only valid as long as the mean number of mutations in the population is close to 0. So this requires, in particular, that the number of individuals that have acquired mutations stays much less than the population size n. And by analyzing this expression when j equals 1, one sees that this condition holds when t is smaller than 1 over s times the log of s over mu, which I'm going to call a sub n. So a sub n is basically how long it takes before most individuals in the population have started to acquire mutations. Now, another question to be concerned about is whether the number of type j individuals in the population can be well approximated by its expectation. Now, second moment arguments tell us that this approximation is fairly accurate up to time a sub n, as long as j is smaller than k sub n, where k sub n is the log of n over the log of s over mu. So basically what's happening here is that for j less than or equal to k sub n, type j individuals are appearing in the population almost right away. So more specifically, for any positive epsilon, the probability that a type j individual has appeared before time epsilon a sub n is tending to 1 as n goes to infinity. However, for j larger than k sub n, we don't necessarily have type j individuals appearing in the population right away. And in fact, the expected number of type j individuals is then dominated by rare events in which a type j mutation occurs much sooner than we expect it to. And when that happens, the number of type j individuals at some later time can be much larger than usual. So the expectation is dominated by those rare events. The actual number is typically much smaller, and so we can't approximate the number of type j individuals by its expectation. We need to come up with another way of studying the evolution of the type j individuals that's going to require some sort of truncation. And so the key idea, which is certainly not new, is to divide the evolution of the type j individuals into stages. So we'll let tau j be the first time when the number of type j minus 1 individuals is at least s over mu. One can argue that typically no type j individual will appear before time tau j. However, between times tau j and tau j plus 1, type j minus 1 individuals will start to acquire a jth mutation, and so the type j population will start to emerge during this period of time. But then after time tau j plus 1, so there are at least s over mu individuals of type j, and at that point the type j population is well established, and further mutations from type j minus 1 to type j will have little additional effect on the overall size of the type j population and can therefore be ignored. Also at this point, the type j population is growing at a fairly predictable rate, and random fluctuations are not affecting the number of type j individuals very much. So in particular, we can approximate the number of type j individuals by this expression here. So s over mu is the number that we have at time tau j plus 1, and we multiply by the exponential of this integral because at time u, the type j population is growing at the rate s, the selective advantage of an individual, times j minus m of u, the difference between j and the mean number of mutations in the population. Now we need to say a little bit more about how the type j population emerges between times tau j and tau j plus 1. So after time tau j, we can approximate the number of type j minus 1 individuals by this expression here. And we're going to let q of t be the difference in the number of mutations between the fittest individual in the population and an individual of average fitness. So then shortly after time tau j, this expression j minus 1 minus m of u will be very close to q of tau j. And so we can approximate xj minus 1 of t by this expression. Basically, the type j minus 1 population is growing exponentially at the rate s times q of tau j. That's measuring the difference between the type j minus 1 individuals and the fitness of a typical individual. So now to calculate the number of type j individuals at time t, we observe that mutations to type j are occurring at rate mu times the number of type j minus 1 individuals in the population. And if such a mutation happens at time u, the expected number of descendants of this mutation alive at time t is given by e to the power s times q of tau j plus 1 times t minus u, where the growth rate is now q of tau j plus 1 because the type j individuals have one additional mutation. So one can then rewrite this expression algebraically this way, and as long as t minus tau j is much larger than 1 over s, we can approximate this integral by 1 over s and get that the number of type j individuals in the population is approximately e to the power s times q of tau j plus 1 times t minus tau j. So we have this expression to the number of type j individuals, and we know by definition that at time tau j plus 1, this number should be approximately s over mu. So just rearranging this expression, we get that tau j plus 1 minus tau j should be approximately 1 over s times q of tau j times the log of s over mu. So that's the difference between the time when type j individuals start to appear and the time when type j plus 1 individuals start to appear. So the reciprocal of that difference is the speed of evolution. Now we're going to argue momentarily that q of tau j is roughly 2 log n over the log of s over mu, and that means that the speed of evolution is roughly 2s log n over the log of s over mu squared. Now other researchers have also tried to estimate the speed of evolution. Desai and Fisher arrived at this expression. Ruzin, Brunet, and Wilk arrived at this expression. It turns out that under the assumptions that I outlined earlier, all three expressions are asymptotically the same. These two just have some extra factors inside the logarithms that turn out to be asymptotically negligible. These other authors also used fairly similar heuristics to the ones that I described. However, they assumed that the population was in a sort of equilibrium, whereas the approach that we're going to take will allow us to see how that equilibrium arises from the initial population. So how then do we estimate this function capital Q? Well, first notice that type J becomes the most common type in the population at approximately the time when the number of type J individuals surpasses the number of type J minus 1 individuals. And just from comparing the approximations that we have for those two quantities, one can derive that that happens around time tau J plus A sub n. So turning this around, this means that the most common type in the population at time t, which should be close to m of t, is approximately the new type that was appearing at approximately time t minus A sub n. And so Q of t, which is the difference in number of mutations between the fittest individual and an average individual, is approximately the number of new types that appear between times t minus A sub n and t. Now we've seen that the rate at which these new types appear is proportional to Q. That is the difference in fitness between the typical individual and the fittest individual. And so Q of A n times t, scaled in this way, is going to be given approximately by this function little q. And we get little q of t by integrating the function little q from t minus 1 to t. That's because we have these new types appearing at a rate proportional to q, and we want to count how many of these new types appear between times t minus a n and t. So under the time scaling by a n, we're going from times t minus 1 to t. Before time 1, we integrate instead from 0 to t, and in that case we can solve the integral equation to get e to the t. Notice that q of 0 is 1, and that's because we have these k sub n types that appear in the very early stages of the process. Now, to figure out what happens asymptotically as t goes to infinity, we use renewal theory. So we can let u of t be the expected number of renewals by time t when the times between renewals are independent random variables having a uniform distribution on 0, 1. Then a calculation using the elementary renewal theorem tells us that u prime of t satisfies this integral equation and therefore is equal to q of t. And since the mean of this uniform distribution is 1/2, this means the long-run rate of renewals is equal to 2, so q of t is converging to 2 as t goes to infinity. And that gives us the asymptotic value for this function capital Q. So here then is the precise result. We'll suppose that assumptions 1 through 3 hold. Then q of a n times t, normalized in this way, converges in probability to little q of t. And this convergence is uniform over compact time intervals as long as the time interval does not contain 1. We also get a similar result for the mean number of mutations in the population. If we speed up time by a factor of a sub n and normalize by dividing by k sub n, or the log of n over the log of s over mu, we get convergence this time to the function little m. Little m of t is 0 up to time 1. That's because the mean number of mutations in the population stays close to 0 until time a sub n. But then after that, the mean number of mutations is basically the number of new types that appeared more than a sub n time units in the past. So we have a 1 to account for the k sub n types that appear essentially right away, and then we integrate the function little q from 0 to t minus 1. The reason why we can't expect convergence when t equals 1 is that the functions q and m are not continuous at 1, and that's because around time a sub n, the mean number of mutations in the population increases rather abruptly from near 0 to near k sub n. Now I want to make a couple of comments here about how this result is proved. So the two core elements of the proof strategy are fairly simple. Between times tau j and tau j plus 1, we approximate the number of type J individuals by a supercritical branching process with immigration. After time tau j plus 1, we show that the fluctuations in the number of type J individuals are small by using second moment arguments that are similar to those used by Durrett and Mayberry. However, a challenge that arises, and that considerably complicates the proof, is that after time tau j plus 1, we want to approximate the number of type J individuals by this expression here. However, that depends on the mean number of mutations in the population, which is itself random, and even worse, it depends in part on xj of u, which is what we're trying to approximate. So the solution to this is to show that the approximation works as long as this process M stays in a tube, and furthermore, we can show that the process M stays in a tube as long as this approximation is valid for all j. So basically, one can show that neither M nor xj can misbehave before the other does. Another challenge is that it's natural to want to think about this process as being in some sort of equilibrium. And indeed, if instead of keeping track of the number of mutations of each individual, we kept track of, say, the difference between the number of mutations of the given individual and the fittest individual in the population, then this would in fact be a positive recurrent Markov chain with a countable state space, and it would converge to a stationary distribution. Unfortunately, I just don't know how to say much rigorously about what this stationary distribution looks like. So the solution, as you've seen, is to start the process from a population with no mutations and just follow this process along over time as it moves towards an equilibrium. Unfortunately, this means that a considerable amount of technical work is required just to track the process up to a point where we're no longer feeling the effects of the initial condition. So that's all I want to say about the speed of evolution. Let's now move on to the question about the distribution of the fitnesses of the individuals in the population at a typical time. So recall that if f is the density of a random variable that has a normal distribution with mean mu and variance sigma squared, the log of f of mu plus L over f of mu is equal to minus L squared over 2 sigma squared. So to see the Gaussian shape in our model, we're going to examine the population at the times when one of the types is near its maximum frequency. So we're going to let gamma sub j be this time, which is basically the time when the number of type j individuals is at its peak. And then we'll let j of t be the value of j for which gamma sub j is closest to a sub n times t. So that basically corresponds to the most common type in the population at time a sub n times t. So then we fix a positive epsilon, an integer L, and a large positive time t. In the denominator here, we're looking at the number of individuals of type j of t evaluated at the time when that number is largest. And in the numerator, we're comparing that to the number of individuals of type j of t plus L. And what the theorem says is that the logarithm of this ratio is approximately minus L squared times this number. And that gives an indication of the Gaussian shape. Now the variance here of the implied Gaussian distribution is 2 log n over the log of s over mu squared, and our assumptions imply that that number is tending to 0 as n goes to infinity. So the distribution of the fitnesses of individuals in the population at a typical time is not truly converging to a Gaussian distribution. It's converging to a point mass, because one type in the population is dominant. Nevertheless, we do at least see Gaussian tail behavior with this L squared showing up there. So next I want to move on to the question about the genealogical structure of the population. And for this we'll need a brief introduction to coalescent processes. So we imagine taking a sample of lowercase n individuals from the current population and following the ancestral lines of these individuals backwards in time. When we do this, these lineages will coalesce until eventually they're all traced back to one common ancestor. And we can represent this process by a stochastic process that takes its values in the set of partitions of the integers 1 through n, where the partition at time t groups together the individuals in the sample that have a common ancestor when we go t units back in time. Now, the classical model of coalescence is Kingman's coalescent, which you've seen earlier in this workshop. Only two lineages ever merge at a time, and each possible transition that involves two lineages merging at a time happens at rate 1. So this is pictured on the left. Here we're tracing back a sample of these 5 individuals, and as we trace them back, first lineages 4 and 5 merge, then 1 and 2 merge, then 3 merges with 4 and 5, and finally the last 2 lineages merge, and at that point we've traced the entire sample back to one common ancestor. Now, about 15 years ago, Pittman and Sagetov introduced a larger family of coalescent processes known as coalescence with multiple mergers that have the property that more than 2 ancestral lines can merge at once. So we could get a picture like the one on the right, where lineages 1 through 4 all merge at the same time. And there are good reasons to believe that coalescence with multiple mergers could describe the genealogy of certain populations undergoing selection. Because if a beneficial mutation occurs in the population and then quickly spreads to a substantial fraction of the population, then when we trace the ancestral lines backwards in time, many lineages should coalesce at approximately the same time, because they're all traced back to the one individual that acquired the beneficial mutation. Now, the most important example of a coalescent with multiple mergers is probably the Bolthausen-Snettman coalescent. So the Bolthausen-Snettman coalescent is defined by the property that whenever we are tracing back B lineages, the rate of each possible transition that involves K of the lineages merging into one is happening at a rate given by this integral here. So in the terminology that Allison was using in the previous talk, this is the lambda coalescent, where lambda has the uniform distribution on 0, 1. Now, for our purposes, the best way to think about the Bolthausen-Snettman coalescent is to see how to construct it from a Poisson point process. So we consider a Poisson point process on the positive reals cross 0, 1, whose intensity measure is given by dt cross p to the minus 2 dp. So then we begin with n lineages at time 0, but then whenever t comma p is a point of this Poisson process, at time t we have a merger event in which each lineage independently participates in the merger with probability p. So we flip a coin for each lineage that comes up heads with probability p and merge all of the lineages whose coin comes up heads. Notice that at the time of one of these merger events, the probability that a particular set of k lineages merges into one is going to be p to the k times 1 minus p to the b minus k. So if we multiply that by p to the minus 2 dp and integrate over p from 0 to 1, we recover the rate of that transition. Now let's suppose that at some time we have a population of size k, and then suppose a new family emerges which rapidly grows to a size of k times x. Well, then the fraction of the population belonging to that family is x over 1 plus x. So if we're tracing ancestral lines backwards in time, roughly a fraction, x over 1 plus x of the lineages, is going to merge at the time when this new family is appearing, because they're all traced back to the individual that started that new large family. Now, we can calculate the rate of mergers in the Bolthausen-Snettman coalescent that impact at least this fraction of lineages. We simply multiply the merger rate p to the minus 2 dp. We integrate that from x over 1 plus x up to 1, and what you get is 1 over x. And this calculation is the key to understanding when we should expect the Bolthausen-Snettman coalescent to describe the genealogy of the population. The Bolthausen-Snettman coalescent will arise when new families whose size is proportional to x times the current population size are appearing at a rate that's proportional to 1 over x. So how then does this show up in our model? So recall we had this approximation to the number of type J individuals in the population at time t. Here I'm writing q sub j in place of q of tau j plus 1. Now most of the time, this type J population will consist of many small families, and no individual mutation from type J minus 1 to type J will be responsible for a significant fraction of the type J population. However, we want to consider the possibility of what could happen if there is an unusually early mutation, where a type J minus 1 individual becomes type J sooner than expected. Well, we know that at time u, mutations to type J are happening at rate mu times the number of type J minus 1 individuals in the population. And we also know that we have a very good approximation to the number of type J minus 1 individuals after time tau j. Now, if such a mutation occurs, there's a very good chance that it will simply die out very quickly. However, by comparisons with a supercritical branching process, we can calculate that with probability approximately s times qj, that's the selective advantage that a type J individual has over a typical individual, this mutation will spread fairly rapidly to a large number of individuals. And if that happens, the number of descendants of this mutation still around at time t will be approximately w over s times qj multiplied by this exponential growth factor. And then by making a calculation using this expression, it's possible to show that if we have a successful mutation at this time here, which is just slightly after time tau j, then the number of descendants of this mutation alive at time t is approximately w times e to the minus b multiplied by this exponential growth factor. And then by comparing this expression to the typical number of type J individuals, we see that indeed when mutations happen this early, the descendants of that mutation are accounting for a significant fraction of the total population of type J individuals. And basically we have enough information here to calculate the probability that there will be such a mutation in which w times e to the minus b is greater than or equal to x, and one calculates that that happens at with probability approximately 1 over qj times 1 over x. And this is the 1 over x that's going to give rise to the Bolthausen-Snittman coalescent. So what happens then if we take a sample of lowercase n individuals from the population at time a sub n times t and follow their ancestral lines backwards in time? Well, because one type typically dominates the population, the sampled individuals will most likely all have the same type. So let's call that type J. And it's very likely that they will all be descended from different type J ancestors at time tau j plus 1, which is approximately a sub n time units in the past. So there will typically be no coalescence during these first a sub n time units. But when we trace these lineages even further back, the type J individuals at time tau j plus 1 will get traced back to type J minus 1 individuals at time tau j. And they will in turn be traced back to type J minus 2 individuals at time tau j minus 1, and so on down the line. Now at each step in this process, it's very likely that all of the individuals that we are tracking will come from different ancestors. However, there's a small probability that because of an unusually early mutation, a group of ancestral lines will merge as they get traced back to the individual that acquired that unusually early mutation. And as we saw on the previous slide, the rates of those mergers are matching the merger rates in the Bolthausen-Snittman coalescent. And I should mention that heuristics very similar to these do appear in particular in this previous paper of Desai, Walczak, and Fisher. So here then is the main result concerning the genealogy of this population. We fix a positive time t and then we fix a time capital T greater than lowercase t plus 2. We take a sample of lowercase n individuals from the population at time a sub n times t, and we're going to follow the ancestral lines of these individuals backwards in time. So we'll let pi n of u be the partition of 1 through n, such that two integers I and j are in the same block of the partition if and only if they have the same, if and only if the ith and jth sampled individuals have the same ancestor at time a sub n times t minus u. So then with probability tending to 1 as the population size goes to infinity, the partition at time 1 is still the partition into singletons. That's because we don't see coalescence in the first a sub n time units. However, after time 1, the finite dimensional distributions of this process pi n are converging as the population size goes to infinity to the finite dimensional distributions of the Bolthausen-Snittmann coalescent. So at this point, I want to go back and say something about the significance of assumption 2, which was basically saying that mutations can't happen too fast. So both the proof and the heuristic argument that I gave rely very heavily on the idea that the type J population, that the evolution of the type J population can be divided into stages, where the type J population becomes well established and is growing exponentially before type J plus 1 individuals start to appear. So in particular, we need to be able to ignore mutations to type J that happen after time tau J plus 1. So recall we had this approximation to the number of type J individuals in the population at time t, and the integrand here is basically capturing the effect of mutations to type J that happen at time u. So in order for our analysis to be valid, we need to be able to ignore mutations that happen after time tau J plus 1. Now the main contribution to this integral is coming when u minus tau J is of the order 1 over s. So our analysis is valid when 1 over s is much smaller than tau J plus 1 minus tau J. And this is equivalent to the condition that the log of n over the log of s over mu squared is going to 0. And this is, in fact, very close to assumption 2. Assumption 2 had an extra log-log factor in it for technical reasons, but the results are probably valid under this slightly weaker condition right here. Now, if the mutation rate is larger, causing this assumption to fail, then what happens is that type J plus 1 individuals start to appear in the population before the type J population becomes fully established and has reached its exponential growth phase. Now, some of the papers in the biology literature indicate that they still expect fairly similar results when this is the case. And because the variance sigma n squared is going to infinity in this regime, we may in fact be able to get a true Gaussian traveling wave in that case. However, it's clear that at least important aspects of the argument would be quite different when this assumption fails to hold. And at the moment, I don't know how to treat the case with these faster mutation rates in a rigorous way. Now also, I want to end then by making some connections to other work. So this isn't the first time that the Bolthausen-Snittmann coalescent has arisen in connection with a population involving selection. One gets a similar result for a model that's derived from branching Brownian motion with absorption. So in this model, we begin with some configuration of particles to the right of the origin. Each particle independently moves according to one-dimensional Brownian motion with a drift to the left of nu sub n, which we take to be a little bit less than the square root of 2. Each particle splits into 2 at rate 1, and particles are killed when they reach the origin. So in this story, we think of particles as representing individuals in a population. The position of a particle corresponds to the fitness of the individual. Branching events, of course, correspond to births. The absorption at 0 models the deaths of individuals whose fitness gets too low. And the particles are moving in time because the fitness of individuals is changing from one generation to the next. So it turns out that the Bolthausen-Snittmann coalescent does describe the genealogy of the particles in this model. that was deduced heuristically in 2006 by Brunet, Derrida, Mueller, and Meunier, and later it was established rigorously by Julian Baristicki, Nathaniel Baristicki, and myself under certain conditions on the initial population. Now, one of the important differences between the two models is that in branching Brownian motion with absorption, all of the individuals have the same birth rate, but individuals with very low fitness are killed. Whereas in the model that I presented today, all of the individuals have the same death rate, but individuals with higher fitness have a higher birth rate. And this may seem like a fairly small difference, but it does lead to very substantial differences in how the two classes of models behave. For example, in branching Brownian motion with absorption, the speed of evolution is measured by the drift nu sub n that's required to keep the size of the population relatively stable, so that we have roughly order n particles in the system at all times. And that turns out to be the square root of 2 minus a correction of order log n to the minus 2. So this sort of behavior with a log n to the minus 2 rate of convergence to a limit was first observed by Brunet and Derrida in the late 90s and has recently been proved rigorously by Berard and Guerre in a discrete time population model, by Mueller, Mitnick, and Quastel for the FKPP equation with noise, and by Pascal Maillard for a variant of branching Brownian motion where there are always exactly n particles in the system. However, the model that I described today certainly does not exhibit this kind of behavior. Also, in branching Brownian motion with absorption, the density of particles near y is roughly proportional to an exponential decay term multiplied by a sine function. In particular, we don't see anything like the Gaussian shape that we saw in the model that we looked at today. And also in the branching Brownian motion with absorption, the time that it takes for two lineages to merge, or the time that we have to look back to find the common ancestor of two particles, is of the order log n cubed, which is quite different from the time scaling by a sub n that we saw today. So these are very different models, and consequently I find it mildly surprising that the Bolthausen-Schnittmann coalescent does describe the genealogy in both models, especially because at the moment I don't have a unified explanation for why the Bolthausen-Schnittmann coalescent should arise in both models. That is, the core calculation that produces the x to the minus 1 is different for the two models. So finally, I want to make a connection to a simpler model involving a two-type branching process. So let's suppose we have type 1 individuals that are growing exponentially, so the number of individuals at time t is roughly a constant times e to the lambda t. So this could be, for example, a supercritical branching process that has managed to survive. And let's say that a type 1 individual gives birth to a type 2 individual at rate mu, and then type 2 individuals give birth at rate b and die at rate d, and we want type 2 individuals to have a selective advantage, so we'll insist that b minus d is equal to lambda plus s, where s is strictly positive. Now then one can do a calculation to see that when t is large, the sizes of the type 2 families, where by a family I just mean a group of individuals descended from the same mutation, so the sizes of those families, properly scaled, can be approximated by a Poisson process on the positive real line with intensity x to the minus alpha minus 1, where alpha is lambda over lambda plus s. And it follows from this that the total number of type 2 individuals has approximately a stable law of index alpha, and the distribution of the normalized family sizes, so we normalize the family sizes so that they sum to 1, the distribution of those normalized family sizes is approximately Poisson-Dirichlet with parameters alpha and 0. So these observations appear in the papers of Durrett and Moseley, and Durrett, Fu, Leader, Mayberry, and Maichor, who were studying a branching process model of tumor growth. And they also came up independently in this paper of Leviang, who was studying a branching process model of HIV resistance. And it was actually, right, so we have these observations, and also if we consider the Bolthausen-Snittman coalescent started with n lineages, then it's well known that as n goes to infinity, the distribution of the normalized block sizes of the process at time t converges to the Poisson-Dirichlet distribution with parameters e to the minus t and 0. So these observations suggest that if we allow the selective advantage s to tend to 0, but then we allow beneficial mutations to happen repeatedly, the distribution of the population should be given by the Bolthausen-Snittman coalescent. And consequently, it was actually the appearance of the stable laws in the Poisson-Dirichlet distribution in these three papers, which appeared before the work of Desai, Walczak, and Fisher, and Neher and Helischak, that originally led me to conjecture that the Bolthausen-Snittman coalescent should describe the genealogy in the model that we looked at today. And I'll stop there. Thank you.
Is there any hope of seeing this Gaussian travelling wave in a rigorous model?
So you mean not just the Gaussian tail behavior, but basically you want to be able to handle rigorously the case of faster mutation rates so that you really will converge to a Gaussian rather than this point mass with Gaussian tails. Yes, I think there's hope. One just has to solve the case with the faster mutation rates, but that is, I believe, harder than this case where the mutation rate is slower. The challenge there is that you don't get, I don't think you're going to get the exponentially growing population. So here, when we study the emergence of type J individuals, the type J minus 1 individuals are growing exponentially because they've already had the mutations that are going to create the type J minus 1 population. When you have the faster mutations, we're already getting the type J mutations at the same time that type J minus 1 mutations are still happening. So the type J minus 1 population, instead of growing exponentially, you've got this exponential growth from the selection plus even further growth because additional mutations are still coming in. And so I just don't know at the moment how to figure out the rate of growth of the type J minus 1 population at the time that the type J population is appearing. And so that's just kind of a stumbling block at the moment. But I've sort of been focused on trying to write up this case, and I haven't really worked really strongly on the case of faster mutation rates. So there's hope, but there's a real stumbling block, a real obstacle to get over.
Do you think that the genealogy might also have a nice description in different parameter regimes, such as this spread out case where the types of spread out?
Yeah, I see no reason to believe the genealogy shouldn't have a nice description. The paper of Desai, Walczak, and Fisher, they don't really indicate that there should be this restriction on the parameters. So as far as I can tell, they're sort of thinking that it should still be Bolthausen-Snittman. My intuition is a little different. It seems to me that for this reason, once you give up the exponential growth of the type J minus 1 population when the type J population is coming in, it seems to me you might lose the Bolthausen-Snittman coalescent. But I'm not sure about that. It could be I'm just looking at it at the wrong scale and the Bolthausen-Snittman will still appear. So I don't know what the genealogy will be in that case.
It would be interesting if other particular lambda coalescents did appear, of course.
Yes, it would be nice to see something else besides just the Bolthausen-Snittman again, but we'll see.